In today's math tutorial, we're going to deal with more elementary concepts. In this case, it will be exponents and logarithms. So we're going to start with what an exponential is. Then we're going to offer a real-life example of problems that deal with exponentials. Then we're going to show some properties of exponentials and how to simplify exponentials. And we will translate exponentials to logarithms and also take a look at its properties. Okay, so a very easy example for exponential functions is cell division. So for example, we start off with one cell, and in each generation the cell will divide into two new cells. So for example, here we're in generation 0, and when we pass to the first generation we will have two cells. Now each cell here will undergo another generation in which it will divide into two other cells. So two cells turn into 4 cells, and then 4 cells will turn into 8 cells. And if we continue, then we will realize that the way this exponential function grows is 2 to the power of the variable. So in this case, the cell division would be 2 to the power of x, being x the number of generations that we're talking about. So here we can see that some bacteria are dividing, and we can see that the population is growing exponentially. This is due to the fact that each cell divides into two new ones.
Now, when we're talking about exponentials, we need to take some properties into account in order to make the calculations easier. So, for example, if we have a to the power of a number or a variable or whatever times that same number a constant a, times to the power of something else, is pretty much the same as saying I have that same constant a to the power of the sum of these two. By the same logic, if we are dividing, it will end up being a subtraction from the top one minus the bottom one. And then here it gets a bit trickier, because when we have a to the power of r over n, it's like if we had square root of 2, we can write it as 2 to the power of 1/2. So then the n would be the nth root of a to the power of r. Also, if we have a power that is affecting a whole other number, then the exponents end up multiplying. So a to the power of r times m, and if the power is negative, it will end up being 1 over a to the power of r. Okay, so so we have seen that the structure of an exponential is y equals a to the power of x, even though this is like correct, strictly speaking, when we're dealing with science and we want to be able to interconvert numbers more easily, we usually use a tool that is a logarithm, that is basically a translation from this expression. And the expression is like this. Notice that I have kept the same variables, so just so that you know where each variable goes. So a neat trick to remember this is that whatever is a base on the exponential is still going to be a base on the logarithm. And some things that you need to take into account is that since logarithms are so commonly used in science, sometimes for certain cases we use abbreviations for them. So if, for example, they just simply say log of something, the base in here actually means it's 10. And if instead of writing log, they just write ln, which stands for natural logarithm, they actually mean that the base is number e. And you should be aware of this, because if not, you will not be able to easily solve some problems. Now, if we jump into the properties, we have this diagram over here that works very easily, and I will explain to you now. What is represented in the circles is what is inside the logarithm. So for example, imagine that we have log of 5 cubed. So that would mean that we would have inside the logarithms 5 to the power of 3. So how this diagram works is that the arrow represents in which form the number goes outside of the logarithm. So here it's as an exponent, so it goes out as multiplying. So then the 3 will go out multiplying. So this equivalence here is actually correct. The same would work if we are working with a square root. If it was a square root of 5 inside the logarithm, it would actually go outside dividing by 2. Also because you can interpret it as to the power of 1/2, and then the 1/2 goes out of the logarithm. And then same goes for the product. So if you have 3.5 times 5, then it's the same as saying log of 3 plus log of 5, because the same logic goes with the next arrow. And also if it's dividing, it will end up subtracting. So that's an easy way to remember it. And these properties that I have just explained actually only deal with what is inside of the logarithm, but doesn't really deal with the value of the base of the logarithm. And for that we actually have the change of base, which is a simple expression that is just that log base b from a equals log from x, being x whatever value you want it to be, of a divided by the log of that same x, but from the previous base. And then that's a neat way to actually translate this. So for example, if you had the log of e squared, and you want to translate this into a natural logarithm, first, well, you would have to take the 2 and take it out, and then you would have to make the change of base. So if you want to change it to a base of e, then it will be ln, meaning that we're talking about a base of e, and then it will be ln of e divided by ln of the base. Because it's not specified and it's in log, it's actually 10. And then the 2 would be multiplying everything. And if you're familiar with all of these properties and you're able to deal with them naturally, then you should be able to do well in exponential and logarithm exercises.
So when we deal with logarithms, we need to be aware of the kind of notation that they use. So normally when they just use log as log and they don't add any number as a base, they usually mean that the base is of 10. Another way to express a logarithm that they use is just using ln, which stands for natural logarithm, and this means that the base is e, and if the logarithm has any kind of base that is different from these two, then they will specify which kind of base it is, and they will use the log to refer to the logarithm.